We're compressing months of fragmented discourse into an actionable lens. Welcome to AI on AI. Today we're tackling defining AGI with psychometrics, agents, and what it means for your roadmap. No pop quiz.
From a cognition angle, AGI means matching a well-educated adult across 10 broad abilities, not just acing math or trivia.
From the modeling side, the profile is jagged, great knowledge, weak long-term memory, and uneven reasoning, especially under distribution shift.
And from a business lens, clarity beats vibes. You need a yardstick that ties to risk, cost, and deployment readiness.
Right and safety-wise, hallucinations, memory retention, and accountability matter as much as benchmark scores.
Engineering reality check. Long context windows help, but it's like debugging spaghetti code in the dark, slow, and brittle.
Strategically, the winners will align capability gaps with use cases. Think of AI as an engine whose horsepower is capped by the weakest cylinder.
In practice, teams want assistants that remember preferences, handle docs, and talk, without awkward silences.
Let's unpack those 10 abilities. Where are models weakest, and why does that matter?
Long-term memory storage is the big missing piece. Without it, every session is amnesia, like reliving the same day.
One fix is integrated memory modules, lightweight adapters, or online learning, plus rehearsal to avoid catastrophic forgetting.
Let me push back, expert 2. Constant weight updates complicate safety and ops, so we lean on episodic stores with indexing and recency.
And that invites privacy questions. What stays, what's purged, and how consent and retention policies are enforced.
Product heuristic, good input, good output. Pair RAG with strict citation and refusal behaviors to keep retrieval honest.
Customer support is a great example. Agents need to learn tone and sign-offs across sessions without copying sensitive data.
The economics favor these narrow wedges. Compounding gains beat moonshots, especially in regulated sectors.
Switching to on-the-spot reasoning. Induction, deduction, planning. How close are we?
Reasoners with tool use, verifiers, and chain of thought help, but they still wobble on novel puzzles and sparse feedback tasks.
Psychometric tests show adaptation is fragile. It's like doing surgery with oven mitts, coordination's missing.
Tooling helps. Code execution, search, and planners act like a multi-tool, but orchestration latency adds friction.
We shipped a supply chain planner prototype. It respected constraints but needed a classical solver to guarantee feasibility.
Exactly, hybrid systems, learned models plus optimization, beat pure LLM improvisation for commitments and SLAs.
What about multimodality, vision and audio, now that recent releases natively handle images and speech?
Perception is improving, yet visual reasoning and video understanding lag. Intuitive physics and anomaly detection remain brittle.
A well-validated cognitive framework suggests mental rotation, spatial scanning, and phonetic coding are distinct muscles, and several are undertrained.
Voice UX adds compliance wrinkles. Consent, accents, and latency expectations can make or break adoption.
We budget latency like a chef plates courses. Streaming ASR, incremental decoding, and half-duplex turn-taking keep conversations snappy.
Real-world wins include radiology triage and meeting copilots that transcribe, summarize, and extract action items accurately.
Let's hit retrieval and hallucinations. How do you reduce confabulation without killing creativity?
Use RAG as scaffolding, not a crutch. Trust but verify with citations, checker models, and user-facing uncertainty.
Contrarian take. Some hallucination is productive for ideation, but in finance or health, it's a non-starter, root by risk.
Building on Expert 4, calibrate confidence, allow abstention, and separate retrieval from generation so the system knows when it's guessing.
And crucially, measure retrieval precision explicitly, not just fluency. Speed without accuracy is a trap.
Recent developments. What's changed in the last few months that matters here?
Longer context windows landed. A new long context benchmark revealed degradation with length, and regulators floated standardized evaluation frameworks.
Open models got strong with efficient fine-tuning, while tool-use runtimes matured, making multi-step agents less painful.
Practitioners now get built-in memory, calendar, and doc tools in orchestration platforms, though the glue is still sticky.
Before we wrap, predictions. What moves the needle toward genuine generality?
Near term, expect native memory modules with continual learning, plus small specialist models orchestrated as a team of experts.
We also need longitudinal evals, story and movie recall across days to verify true consolidation, not just longer contexts.
For businesses, start with bounded workflows, instrument everything, and remember, measure twice, deploy once.
Governance tip: data minimization, model change logs, and incident drills. Treat AI like an operational system, not a demo.
Engineering mantra: fail fast, learn faster, but only behind guardrails and test harnesses. Chaos testing catches agentic surprises.
Macro view augmentation leads, not replacement. Invest in training, process redesign, and resilience.
And hey, until agents truly remember, keep your checklists handy and don't let them order your coffee again.
That's our show, defining AGI with real tests, not wishful thinking. Thanks for listening, and we'll see you next time. Up next, a brief summary of the key takeaways.
Narrated by the AI voice of Shri, the central question is how to define and measure artificial general intelligence in a concrete, testable way. The proposed definition says artificial general intelligence matches the cognitive versatility and proficiency of a well-educated adult. The method grounds evaluation in Cattell-Horn-Carroll theory of human cognition. That theory maps intelligence into broad and narrow abilities based on decades of studies that measure mental skills. The framework tests 10 domains across knowledge, language, mathematics, reasoning, memory, perception, and speed. General knowledge covers common sense, science, social science, history, and culture. Reading and writing measure comprehension, composition, and correct usage. Mathematical ability spans arithmetic, algebra, geometry, probability, and calculus. On-the-spot reasoning means solving new problems flexibly without relying only on learned routines. Working memory means holding and manipulating information in active attention. Long-term memory storage means stably learning and consolidating new information over time. Long-term memory retrieval means accessing stored knowledge quickly and precisely. Visual processing measures perception, generation, reasoning, and spatial scanning using images and video. Auditory processing covers phonetic skills, speech recognition, rhythm, musical judgment, and natural-sounding voice. Speed measures how quickly simple cognitive tasks are performed across different inputs. Each domain receives equal weight to emphasize breadth. The framework reports a single artificial general intelligence score from 0 to 100%. 100% means matching the cognitive profile of a well-educated adult. The evaluation adapts well-validated human cognitive tests into tasks that artificial systems can attempt. The results show a jagged cognitive profile in current systems. Strengths include general knowledge, reading and writing, and mathematics. Weaknesses include long-term memory storage, several forms of visual reasoning, some auditory skills, and speed across images, audio, and text. Long-term memory storage remains near zero for leading systems tested. One widely used model scored 27% overall on the Artificial General Intelligence score. Its successor scored 58% overall on the same score. The newer systems show strong mathematics and improved perception and voice, yet key gaps remain. Capability contortions are workarounds that mask weaknesses. Many systems rely on very long contexts to mimic persistence over time. That workaround strains computation, overloads the system, and fails for tasks that span days or weeks. Another workaround connects the system to external search tools to fetch facts. This hides problems with internal retrieval and the absence of a lasting personal memory. Hallucinations mean the system confidently invents facts or mixes up details. The framework targets human-level cognition, not economic value or physical performance. Abilities interact, so bottlenecks can limit overall performance like weak parts in an engine. Equal weighting and task choices are design decisions that others may revise. A single high score can hide failures if a crucial component is missing. Evaluators should test under small changes in wording to reduce training contamination. The approach is not a static dataset and invites manual grading by independent teams. Open questions include how to build durable long-term memory and precise retrieval. Other challenges include robust visual reasoning, richer auditory skills, and faster processing across images, audio, and text. Future work could add culture-aware tests and alternative weighting schemes. A concrete, shared definition can focus research, clarify timelines, and inform safety planning. Enjoyed the discussion? Pass it along to someone wrestling with these challenges so they can accelerate too.